Hello and welcome to the 23rd webinar in 12D's Industry Solutions webinar series. My name is Lisa Stewart and I'm the Marketing and Communications Coordinator at 12D Solutions. Our Industry Solutions webinars are designed to provide insights into overcoming challenges in an evolving industry in more effective and efficient ways. We'll keep running these webinars regularly and recording them for posting on our YouTube channel with links through our website. Our first 22 webinars from this Industry Solutions series, as well as 21 webinars from our training series, are available online if you missed those. While we wait for everyone to finish joining, I'll pop up a polling question. You'll have about 30 seconds to enter your estimate of the size of the specified storage tank, and then I'll show the results. Well, look at that. I'm glad to see we all know why we're watching this webinar. Welcome, everyone. Okay, let's get started. During this live presentation, you'll be able to type your questions along the way, as shown on the screen, and we'll answer as many as possible throughout the webinar. At the end, I'll also read out some of your questions to the presenter if there's time. Today's webinar, Underground Storage Tanks, will be presented by Rob Graham, our resident water resources engineer, with almost 20 years here at 12D and over 30 years of experience in the industry. In today's talk, Rob will take you through two examples of 12D model dynamic drainage in action, one with storage via an underground tank, and the second using box culverts. Over to you, Rob.
Great. Thank you very much, Lisa. Good afternoon, good morning, or good evening, depending on where you are in the world. Today we're going to go through a very important part of stormwater drainage. Anytime we do change our natural environment, and unfortunately usually involves putting some concrete over some very nice beautiful land, we increase the runoff, and part of our building process is to create some sort of storage so that we can return the peak discharges and hold back some of the water. So that we don't cause downstream flooding. So that's just a very brief introduction to the whole idea of why we're doing storage on site. Often your choices are either underground tanks or above ground. Usually it's a question of area. If you don't have the area for the above ground storage, you're going to be looking for underground options. So with that brief introduction, let's jump into 12D and take a look at how we would create some underground storage tanks. So I've got a project in here. If any of you have gone to 12D's training, you might recognize the training data set. Our plan is we've got a building area here highlighted in gray, and I'd like to put a storage tank there to take the water off that and then discharge back into the system. The quickest way to create the underground storage tanks is to read in a storage tank already created from our library. To do this, we'll go up to File, down to Data Input, head across to 12D, and we'll go to the 12DA library. Inside the 12DA library, there is a drainage branch, and underneath our drainage branch, there's a storage tank option. If I make this a little bit bigger so you can see that storage tank, the idea is that there's a tank up here, and there's several different control devices. It's a little hard to see on here, but I'm going to import it in a moment, and we'll take a close look. Now, because I'm not bringing this into an existing system already, I'm going to use the models from the file. Inside 12D drainage, all of our hydrology, defaults, that sort of thing is all stored as model attributes. So they're all going to come in when I put on this tick box. I'm going to use a prefix for the models that come in. I'm going to call it tank space. And then I would like them to go and select the spot where they're going to be inserted. Now, I'm going to do that by looking at that red X there, and I'm going to go select a position on the screen. Now, I've gone and put a little marker on for myself so I get the location at least close to where I want it. And then the next thing that happens is I wouldn't mind rotating this just a little bit so that the storage tank would line up with my building on the southern side. If I want to do a bit of a rotation on that, I can go get the angle. So if I do add a point and ask for my angle, I can go measure the bottom line of my building, and it's going to give me the angle relative to 0. So that's the mathematical angle. And to turn that into a rotation, I'm going to take 360 degrees and minus that. So that's going to rotate it clockwise, approximately 11.5 degrees, almost 12, and line it up with my building. So once I put in those parameters, I can come down here and say import. It's going to add that model in, and we're going to add it on by looking for a model that begins with tank. So I'm going to go up here and type in tank, and then there's the one I'm looking for, the tank 12D stormwater storage. We'll add that onto the view. So there's what we're looking at. That's the stock standard tank out of our library. This tank itself is set up with its design parameters so that it will float up and down with your design tins. So the first thing I'm going to do is to switch over to the design tins that are used in this model. And that involves the drainage network editor. So if you're looking for the drainage network editor, I tend to take it off the toolbar. So right underneath the railway tracks, which are very easy to see, is our button for the drainage network editor. And I'm going to come across and I'm going to select my stormwater tank. So the very first thing I said I wanted to do was to go change my data terrain model that's being used. So the finished surface tin in this project is going to be called combined, and I also want a natural surface tin, which is going to be called survey. You might have noticed those great big red bars when I selected that. That indicates that those models have been, especially the survey one down here, has been shared into this. The capability for 12D model to share the work between designers so the work can all go simultaneously is a very important part of 12D. So we've got our design all ready to go there. All I have to do to adjust my levels is to come and do a set pit details and then go back and do a regrade pipes. Let's take a look at this in a section view now. I'm going to do a window. I'll come down here to tile vertical. And to give myself a little more real estate, I'll minimize that. Let's do that again, do another tile vertical. And I'm going to come across and profile my drainage system. So what I'm looking at here is there's three different paths. First of all, there's the weir itself. The weir is my continuous path. So maybe I should show you that one first. Let's go back and say profile again. And I'm going to do a single click here, just downstream of the tank, and it says that's my orifice path. And you notice there where it says name, that's my weir path. That's the one I take a look at. And you can see what we have here is this is the storage tank. The storage tank on the weir path, you can see there's my weir. It goes and drops down into my outlet pipe, which goes down to my outlet down here. Now, when you're looking at the weir path, you can also see the elevation of two other flow paths. There's a pipe that goes across here, and there's also an orifice down here across the bottom. So what I'd like to do is I'm going to go take a closer look at those to give you an idea of what's been taken out of the library. So first of all, let's take a look at the one that we've selected. So if I go back to my pick button, you'll notice that when I pick in this area just downstream, that's the easiest way for me to move through the three different flow paths. So this first flow path that I'm selecting is the orifice. So if I move across to my pipe tab, you'll notice that it's got an orifice with a 0.075, so 75 millimeter diameter. And what makes it an orifice is this mode across here. Because for our conduits inside our 12D dynamic drainage, you've got quite a selection of what your conduit represents. So in our case, it's a side orifice, and we'll be looking for a discharge coefficient for that orifice. When we do our plotting or we do our viewing of graphs, it sure helps a lot if we can have a good name for our pipes. So I'm going to call this one orifice just to help out. So that's the first one. That was the bottom circle that we saw on our section view. Now let's go and select the next one, which is a pipe. So what it has at mid-height, if you take a look across here, we've got the pipe connecting the tank to the outlet control pit. And for that one, I'm going to do the same thing. I'm going to go give that a better name for it so that we can read it and see it on our graphs. And also, I want you to be able to see what it is. Currently, if we take this up here, we've got our pipe tab, and we're looking at a circular pipe with a 150 millimeter diameter, a PVC. Often the reason that you have a mid-height pipe like this is it allows you to do some fine tuning on your when you're trying to meet your pre-site discharges. The third one that we had was our weir. So let me just jump back and take a look at that weir. There's that weir path. Now I'm going to do the same thing again. I'm going to call this one weir so that when we see it on our graphs, we'll recognize it. And this one is a rectangular weir. So if we go and take a look up here, we've got our mode set to weir, and we've got a height of 300 and a width set of 1.5. So quite a wide weir. Later, we're going to come back and make that a little bit smaller. Now, having a height of a weir, often people wonder, well, that's kind of a strange thing to do. What happens with underground storage tanks, if the HGL was ever to reach that top height, it would change the formula, and we'd switch over from a weir coefficient over and calculations over to orifice, and the orifice coefficient would be at 0.6. So that's the reason that we have a height for our weir, especially important when we're doing underground tanks. All right, well, enough about the basic tank itself. It's probably time that we take a look at some of the hydrology so that we can see what the pre-site discharge is. So what I'm going to do is I'm going to go across to my global tab, and on our global tabs under utility models, we have what's called a catchment file. And I'm going to select my catchment file, and this defines which catchment polygons and which models will be linked to our storage tank. Just going to open that up for you. And I've chosen to put my buildings into set number 2. And that's the only polygons I'm using right now. And they're in a model called building catchments. And that's that catchment you see up here. When you're using building catchments, you'll often want to use that as a hole. So actually you'll cut a hole out of the lot catchment if the lot is draining separately down to another pit. And if we have time near the end, we can talk about how you create holes inside your superstrings. So that's our catchment that we have there. The button that does the linkings is down here with the set catchments. So when I do a set catchments button there, it's also going to do a validation on some of the data. If we're going to be putting in a tank, the KU method or the losses are important ones. And generally for a tank like this, the water would be quite still at the entrance. So I'm going to go put a direct value of low velocity at the entrance for that. Now, if you felt a more appropriate number would be different, you'd go ahead and type it in. But what we're trying to indicate here is that for these conditions, using the Missouri hair charts would not be the way to go. All right, back to the catchment tabs. So catchment, set number 2, and now we can do our set catchments. And this one hasn't come back and automatically selected it. So what we need to do is use our pick button, come back and select that. And then the next time we do a set catchments, it will go calculate the catchment areas. So you can see our building area for this one is 0.17 of a hectare. Well, our polling question at the beginning was, well, what size of tank do you think we would need for a building of this size? A very good answer to that would be too vague, because it does depend where you are in the world. It depends a great deal on your IFD, the magnitude of your rainfall, but also the temporal patterns, whether the flow is spread out quite a bit over time or if you get very sharp peaks. So really, I suppose the best answer would be too vague. But once you've done a few tanks in an area and you start to get an idea of the sizes, you might find that if you happen to be, and I'm going to slip over here to my global tab, if you happen to be in Cairns, all right, so we're up in the northern part of Australia where they get very, very heavy rainfalls, you might find that you need a storage tank that's approximately 3 to 4% of your area. So with that in mind, if I was to come back to my pit tab right now, if I want to set the size of my storage tank, all I have to do is set the dimensions for my stormwater pit, which is a pretty easy thing to do. So if I didn't have my calculator nearby, I could go and take if we went 0.17 and we multiplied that by 10,000, okay, that would get us up into the square meters. Then we'd multiply that by 0.035. And you see we were looking at roughly 60 square meter tank. So we're looking at a very big tank for this site. Now the plan is, that's my plan area. If I'm going to make my tank about 2 meters wide, it only needs to be about 30 meters long. I can do that, divide by 2 in my head. So that's going to be my initial sizing for my tank. The next thing I'd like to do is to go down and fix an unfortunate mistake in our outlet for our channels from our discharge control pit. This pipe down here, we wanted that to be a conduit. And when I went through this, I noticed that the one we were shipping had it as a side orifice. So let's just take a moment and put that back to a conduit. So what happens is, out of this discharge control pit, we've got a 450 pipe that's going to be taking the water back to our stormwater system. So I'm glad that we've got that fixed up and out of the way. All right, next step. If we go hit the apply button on that, or you'll see that all of a sudden we can see the full size of that tank. Well, that's probably not the location we want the tank. We need to pick this tank and move it a little bit under the base of the building. Now, the best tool that we have for picking and moving that is our utilities translate option. So let me just take you into that and show you what I would do for my translating that tank in the upstream direction. I'll go up to my utilities, down to H to Z, and move across to translate. The translate option that I want to use is the rectangle, because when you use a rectangle, you get the option to only move the selected vertices, which is very handy. So I'll come down here to my rectangle now. What I'm going to do is I'm going to draw a rectangle just around where it says tank. That's the center of my tank. And it's going to tell me that I've gone and selected the elements down here to move. Now it says I've selected them from 2 models. I might just jump back here and see. It'll be fine. There's 2 things that will get moved across. Wasn't so much concerned about the marker that I had in there, but that's fine if that moves as well. Now what I'd like to do is to move this. So I'm going to use the replace option, and then I'm up to the moment where I'm trying to specify how far I want to move it. Well, I get to use this selection here where I get to pick the end of my pipe. That's what I want to move. And what I'd like to do is to bring that back so that it's just on the other side of my flow paths. And then if I go translate on that and then go and zoom out a little bit, you'll see that it's in a much better spot. At this point, you might be a little concerned that they don't quite match up. Fortunately, the next time we touch this with our drainage network editor, it's going to recognize that we've moved that. And so the next time I do an apply, it will go and make sure that those flow paths are connected back up. So what I've done there is I've gone and made an initial estimate, my tank size of being 60 square meters. And now what I'd like to do is to go through and put that pre-site hydrology on it, get an idea of what type of flows we're looking at for cans. So I'm going to move back to my catchment tab, head back to that set number 2, and I'm going to make it 0% impervious. So I'm looking at a completely grassed site. Now when I do this, I'm going to want to come down here and select the soil types. And for this case, I'm going to choose slow infiltration clays. That would, of course, you'd have to have some site knowledge. The second option is the storage. When we're using the Ilsak's hydrology method, the infiltration is the first loss that goes down into the ground. Any water that does not go into the ground will pond up to the surface before it starts to flow off. So that's what that 10 millimeters is representing, is there. So now I've also, if I come up here, I can check to see my time of concentration for my pre-site. So it's approximately 10 minutes for this site. So let's go take a look at this. We'll run the hydrology. So I'm going to go across to my analysis tab. And the first one I'm going to run is the 2-year storm. The CAN's hydro file, you notice, is in our library. What I've done instead is I've gone and taken a local copy of the CAN's one. And if I go open that up, you'll see what I've done for my temporal patterns is I've turned on all of the short temporal patterns. And the reason I have to do this is that often the peak discharges off a site will come from the 25-minute storm. However, later when we have to analyze a basin, it's the longer storms that have greater volumes that become critical. So essentially, I'm selecting all the shorter storms until I get an idea of which is going to be my critical storms. All right, so that was just a quick look into the hydro file. I've gone and selected that one. Now I'm ready to come and do my run. The The first run I'm going to do is for my 2-year return period. So let's come down and hit the run button on that. So when we select that run, you'll notice that several different windows are popping up and disappearing. It's a very, very small network, so they all run very quickly. And it's calculating and storing the peak results from each one of those storms. So we'll just give it just a moment to finish that one. And when it's all finished, we're ready to go back to our editor and start taking a look at the results. We can get our real estate back there. Now, to look at the results, the numbers are good just to look at peaks, but often when you're working with stormwater tanks, you want to see the full hydrographs. You want to see how things are changing with time. So what I'm going to do is move over across to my results tab, and I've run a whole series of design storms. So I want to see the results from all of my design storms. And what I'd be interested in is this pre-site hydrology that I've done. So on the pit graph, I'm going to come down here and I'm going to ask for my catchment flows. Now when this first pops up, it's a little bit small for everyone to see on their screen. So what I'm going to do is go back to my global tab for my display, and I'm going to make these a little bit bigger for everyone to see. So I'm going to make that 1200 by 800 pixels. And if I select the apply button, because I want that to be effective immediately, I can come back, and every time I ask for my graphs now, they'll be a little bit larger. So recall, this is the pre-site. This is what we're looking at when we have 0% paved. And up here at the top, you'll notice that the 60-minute storm has a bold line through it. That indicates that it's the one that has the critical discharge. So my pre-site discharge from this would be 48 liters per second, resulting from the 60-minute storm. And if I wanted to zoom in closer to get a better look at that, there's the storm that we're referring to. Now, although it is the peak storm, you will notice that there's several of them that are very, very close. So 48 liters per second is our pre-site discharge. So now if we're going to build the building over top of that area, we expect that discharge to rise. So what we'll do is return to our catchment tab, and we're going to change our percent impervious from 0 to 100 to represent the building itself. Now there's a few things that are going to change when we move across here. The first is the time of concentration. It's going to move from 10 minutes down to 5 minutes. So the flows are going to change much more rapidly with the changes in rainfall. The second thing is the storage that we'll have is going to be much smaller on the impervious areas. So I'm going to put that down to 2 millimeters. So now that we have this post-site hydrology, post-development hydrology in, let's go back and rerun that. So I'm going to return to my analysis tab and go run that 2-year once again. Only this time, of course, we're going to be using the new hydrology. Once these storms are finished running, what I'm going to be particularly interested in is to see the difference between the inflow and the outflow from our tanks. And of course, we're going to see that again on the results tab. So we're going to go back to the editor again. And this time I'll go to my results tab once again. And I'm interested in seeing all of my design storms. And I'm wondering which one of the storms is responsible for getting the hydraulic grade line up the highest, which is the one you see here. Now, currently it's being shown as an orange line. That's probably not a great color. I might go back and change my settings for that, for my drainage. And let's make that, instead of an orange, let's make that a yellow as well, just to make that a little bit easier to see and distinguish from the pipe itself, the tank itself. All right, so all the design storms, let's go take a look at the elevations. And what we're going to find here is that it's the 90-minute storm that causes the tank to fill up to the highest elevation. So now I know that the 90-minute storm is the one that's critical. I'm going to return and say, just give me the information about the 90-minute storm. And what I'd like to see is the total inflows and outflows from the tank. Now, one of the things that I mentioned earlier was that with a 5-minute time of concentration, we're going to find that our inflow changes quite rapidly with changes in our temporal pattern, changes in rainfall. The other thing you'll notice, we've got our outflow hydrograph here, which peaks, it comes down, and we get a pretty substantial attenuation in our flow. So it looks like this whole idea of using the tank is a great idea. One of the things that concerns me when I look at this is this area up in here. This is dead storage. What we're trying to do is limit the outflow. And if I could get my outflow hydrograph to be much steeper in this area, I would not waste the storage, which is the area between the inflow and the outflow curves. So I'm going to go back and revisit this. I'm going to say, what can I do to possibly get rid of this discharge at a much earlier stage so I don't need so much volume? So let's close that graph just for a moment, and let's go back and look at our model, and we'll look at it in the section view. And the first thing we'll notice is that 450 pipe that I discussed earlier. It's going to be putting backwater effects onto our orifice, and it will also be putting a backwater effect onto our pipe, limiting the discharge. Now, if I had enough vertical change inside my site, if I was to drop this pipe down, I could get rid of the backwater effects, and my conduits would be able to discharge more water sooner, which will mean a smaller tank. So if you do have the drop, let's look at on your site, let's look at moving that outlet pipe down. Now, the easiest way for us to move that outlet pipe down is just to change the default drop that we use inside 12D. So I'm going to come back across here, and I'm going to pick the through line, which is my weir. And, sorry, pick the orifice because I want the drop off the orifice. And I'm going to go to my pipe tab, look across to my design, and instead of having an invert-to-invert drop of 0 there, what I'm going to do is I'm going to change that to be 0.45, which is the diameter of that pipe. So if I go regrade that, what it's going to do, it's going to push that down. Throughout this presentation, I'm going to be using these design parameters because what I'm trying to do is to keep my tank floating. So that if my data train was to change, then the whole tank would float up and down. And that often happens when you're doing stormwater design. The final surface is not determined until much later on. So having a tank that will float up and down with your data train model is a very quick way if you have to revise it in the future. All right, so that was the first idea to make a smaller tank, was to drop this down on the outside. The next thing I want to take a look at is how much water was going through my different flow paths. So if I was to return to my results, and still the 90-minute storm, but this time instead of looking at the total flows, I want to see each individual. So I'm going to go for all inflows and outflows. So what I'm seeing here now is on the top as a positive flow is my inflow hydrograph to the basin. On the bottom side as negative, I'm seeing my outflow. And the outflow that I'm currently seeing, if you check here, my orifice flow is actually quite small. I'm only getting about 9 liters per second coming out of the orifice. And I'm getting a lot of water coming out of that pipe. So what I'd prefer is if it was the other way around. What I want to do is to get rid of the water out of the orifice quickly so that my tank stays as empty as possible, making more efficient use of storage. So where I plan to go then is let's go back to our pipe tab. Well, we might as well do our orifice first because we're already here. And I'll head to the pipe tab, and I'm going to make that a bigger orifice. So rather than have a 75 millimeter one, let's make it bigger. Let's go up to about 0.125, so almost double. At this point, you've probably realized that, yes, I have run this before and taken a look at it. The guesses I'm using for my sizes are ones from some past experience on this model. So if you were doing it the first time, you might have to guess once or twice what better values would be used. So the idea there is I'm making the orifice bigger. That's going to get rid of the water quicker. So I'm going to make the orifice bigger. I'm probably going to have to make my pipe a little bit smaller. So I'll go back up here and I'm going to my weir. There's my pipe. So my idea is I'm going to go across to my pipe tab and I'm going to make this down to a 100. So we've got a smaller pipe that's going to be taking the water out. So let's go back and do our storm analysis on that and go run that. So once again, last time we were definitely we're attenuating the flows. We had the flows down. Oops. Let's go back and check what we missed on that. Sure. Yes, what happened there was we had the attenuation and flow, but the water level was getting very deep. And I was only running my 2-year storm, and I wanted to get rid of the water more quickly, more efficiently. So when I come back and run it this time, I'm going to expect to get the same discharges, my same attenuation, but the water level is going to be lower. So that was the whole idea behind these small revisions that we've done at the very beginning, making more efficient use of the storage. All right, the next thing we might do then, that we've done that with the 2-year, let's go back and, oops, we'll stay with that one, sorry. Let's go run the 20-year storm. Now I'm moving on for this one just because I could show each one of the results at every iteration step, but then we would probably go a little bit over time on that. So I'm just going to go straight to the 20-year and take a look at what's going to happen with that. What you'll notice is the HGL is almost at the bottom of that weir. So that weir is going to start sending water out far too early. Usually you want to use that overflow weir more towards the 50-year events. So you'll notice here at the 20-year, it's definitely discharging over that weir. And that indicates to me that that weir is too low. So I want to go modify that as well. Let's go take a look at the effect on the discharges, because that's another place that we'll see that. So once again, back to my results, back to see all my design storms. I'm going to check the elevations to find out which one was the critical storm. And the one in bold, yeah, the 60-minute, still the critical one. So let's go take a look at that 60-minute and see where the water's going. So I'm going to take a look at all my inflows and outflows. And once again, you'll see I've got this great big large outflow here, and sure enough, that's the water going over the weir. So if I was to back up just a little bit and look at the total inflows and outflows again, I would see I'm getting almost no attenuation in flow whatsoever because that weir is being used way too early. So our solution to that would be to raise the weir up a little bit. So the way I'm going to do that is, once again, I'm going to go pick that the weir line, and I'm going to use my design parameters again. And so what I'd like to do is I need this to come up a little bit. So I'm going to make my weir a little bit smaller in the vertical. I'm only going to make that 0.2 of a meter. So make that 0.2 of a meter. And I'm also going to make it much narrower. I'm going to make it 0.5 meter wide. So between those two, if I do a regrade pipes, what you'll see is that invert moved up. So now I'm not expecting the water to discharge as soon. And on the 20-minute, I would get far more attenuation. Sorry, on the 20-year ARI, I would expect to get much more attenuation in my flows. So let's go back and run that one more time to see what that's like. We'll head to the analysis. We'll run the 20-minute again. So what I'm expecting now is, because I did not have the water going over the weir, the water level is going to be a little bit higher. I will get a little bit of flow over the weir, but not so much. So we'll just let that one finish. And then if we go back to the editor, and let's once again, now I'm going to just assume for a moment that our 60-minute is going to once again be our critical storm. And now you can see that because we've lowered that down, we're starting to get the attenuation that we're expecting. Now for our 20-year storm, if I went and did the pre-site hydrology for that, I would have found that it was 96 liters per second. So my outflow right now is very close to that. And for a first time iteration through, I think we're very close to our target. So it's working very well at this point. Let's go back and just run this one more time. Now, if this was our project, we might have to check the 50-year as well, but let's just straight to the 100-year to see what's going to happen during our 100-year event when we run this. Now, depending upon what area of the world you're in, sometimes you have to attenuate the 100-year event. Sometimes you just have to pass it safely. And in this case, we're looking at attenuating the 1 in 100 year event. So we want to keep that within our structure. That one's just finished there. If we go back to the editor, I'll just do a quick double check on those elevations again to make sure we're still looking at the critical storm. That critical storm right now is still the 60-minute one. That's sort of what I expected. I didn't expect that to change. And once again, if I start to look at the total inflows and outflows from our basin, I'm getting that attenuation that I'm looking for. Now, my outflow is 128 liters per second compared to 153 coming in. When I did my pre-site discharge, it was 125. So I'm once again, very close to the target. So this is working well. Now, time for a little more refinement. At the beginning, I mentioned that this area inside here at the beginning indicates wasted storage. Okay. If there was a way we could get the water out of there faster without using up any storage, we could make a smaller basin, saving money, and hopefully getting very close to the same characteristics. So what I'm going to do now is we've been using the pit tab, and we've been using the area of the size of the basin to create a stormwater detention. If I want to do some finer tweaking onto this, I can come across here and I can use the Basin tab across here. And this Basin tab can also be used for underground storage. So what my plan here is, I'm going to zoom in a little bit closer. And I'm thinking that if I didn't have any storage at the bottom, if I had my orifice in a small depression inside my tank so that it just got completely wet, then that bottom 150 of my tank wouldn't be needed for storage. And my entire 60 square meter tank could be raised by that 150, saving me a bit of money. So what I can do is I'm going to go back to my main tab for a moment, and I'll notice that the bottom of my sump was at 8.5, well, let's say it's 851. So if I go back to my basin, I can put in my 34.851. So that's 34.851. Let's just double make sure I've got that one right. 34.851, that's the bottom. And I can put in a basin area of 1 square meter. So what I'm indicating there is that there's going to be a very small depressed area of my tank in order to flood my orifice very early on in the storm. So what I'm going to have is only be 1 square meter. What I'm going to do is add on the height of my orifice. Now, if you remember way back earlier on, we made that orifice bigger. We made that orifice 125. So if I add 0.125 onto that, I still want my area to be 1. Okay. Now, there's a few too many decimals inside there for my liking. I'm going to go round that off to 976. When we put our curves in, we always want to make sure that the elevations are increasing. So my next one would be 34.977, and my idea is to make the basin area up to 60. So these values are going to override the values that we've entered for the pit size. Then what I'd like to do is to get up to the top of my basin. Now if I go back and take a look at the top of my basin, that was up at 36.054. So back to here to 36.054. That's still going to be 60. That's going to be the top of my tank. Then what I want to do is that's the very top of my tank. After that, it's going to be reduced now for the very small opening, your manhole in the top of your tank, where if it ever did overtop, it would bubble out and go. So at 36.055, I'm going to put a basin area of 1. So that represents switching from the tank back to the manhole. So the idea of what I want to go through here with you is that you can manually put in the areas to override the size so that you can tweak your design down to a fine amount of detail. Now at this point, if we were to go and do the analysis on this and go run that, I have taken away some of my storage, right? I've raised the bottom of my storage up by 125 mils. So I would expect my discharges to go up just a little bit. So let's just go back and see the effect of raising the bottom of that tank 125 millimeters. All right, that one's just finishing for us. So if we go back to the editor, we'll do the same things that we've done before. We'll head to the results, just do a quick double check that the 60-minute storm is still our critical. And I can't imagine it not being. And sure enough, that's still our critical storm. And if we were to now go back and take a look at the 60-minute storm and take a look at the total inflows and outflows, you'll notice that the outflow has gone up. Okay, it went from 128, I believe we're on last time, to 130. So for 2 liters per second increased discharge, we've just raised the bottom of our tank 125 millimeters. So once again, the concept of making this area between the inflow and the outflow hydrograph as small as possible by using high early discharge mechanisms like I've shown you, we can reduce our storage tank sizes. Well, that's a lot of numbers, a lot of theory, but I think that we've reached the point where we've got a pretty good stormwater tank. So the next thing I'd like to do is to go back and to take this tank design and take a look at how we would do this if instead of building a concrete tank, we wanted to use box culverts to represent that storage volume. So I'm not going to change this live one because I want to keep both. I'm going to go make a copy of this. So I'm going to go up to my models and I'm going to go to my utilities and copy a project model. And my current project is stormwater. I'm going to zoom down here and find my tank model. Should be under uppercase T. There it is. And I'm going to give this a new name when I copy it. I'm going to call it my box culvert storage. And we'll take a copy of that. And that, finish. Let's go turn off our tank and let's go back and add on our box culvert storage. So now what I want to do is to take you through the step that's of changing this tank back over to box culverts. So the first thing is this very large tank is going to change to be a head wall structure for our culverts. So the very first thing I want to do is go resize that tank. So I'm going to grab my drainage network editor again. I'm going to go pick that tank, come back to my pit tab, and where I had made that 30 meters before, I'm going to bring that down to 1 meter. And if we go hit that, and we'll hit the apply button onto that. Oops, get my mouse better. Okay. That brings us back down to the very small tank. When we go and move our tanks, it's a really good idea to move the tanks before we resize them. So what I'm going to do is just skip over one extra spot for a moment. I'm going to leave these nice and long, and I'm also getting a little concerned about the time. So I'm just going to add my box culvert straight onto the end of these relatively long conduits right now. The length of a weir and an orifice doesn't matter because an orifice and a weir do not have any storage volumes. We're going to get a little bit of extra storage in that 100 millimeter pipe, but not very much. So in the interest of time, I'm just going to go straight on to the next step where I put my box culverts upstream. So I'm going to come across to strings, points edit, append, and I'm going to go select the upstream end of my tank. And I want to go select my weir. And I'm going to make it just a little bit bigger. So not a lot, just a little bit, but I'm going to be a little focused on the direction of it. We've got a great tool inside 12D for extending pipes to exact lengths. And that option's under Design, Drainage, Sewer, down to More, and it's called Extend Pipe and Culvert. So what I'm going to do is go pick that pipe that I'm looking at extending, and I'm going to extend it as 1.2 meters. Box culverts never quite join together, so I'm going to put in a 10 millimeter gap length. And what I'm looking for, if I'm going to get back out to my 60 square meters, if my box culverts are 2 meters wide, I have to get that length back up to 30. So what I'm going to do is come here and say that I want to have 23 of these pipes. And if I hit the enter key after that, it tells me that's going to be 28 meters long. And you might be wondering, well, why aren't I going to 24? These tanks, they're 1 meter long. So I'm getting 2 square meters out of this tank. And when I've got another tank at the upstream end, I'm getting 2 square meters there. So I want to make sure that I do not double count the storage. So that's why I'm going to just my 28 rather than 30. So if I wanted to make these bigger, I can just go process that. Essentially, that's going to zoom that out so that I've got the length that I'm looking for. And I'm ready to go put the data onto the box culverts. So off to my drainage network editor one more time. Now the name new, oops, get a little bit closer there. Start down here maybe. Okay, so on that tank, there's a couple of things I wanted to be sure. First of all, when we did that conversion, the basin data has definitely been removed, so we're good on that front. And I'd also like to go back to the main and just to make sure that we go put that KU method back to direct with a value of 0 for that one. And then I'm going to head back to the left and do the very same thing for the upstream. Now it tells me that I'm going to have a different cover RL mode, but that's fine. Go update that. And I want to change my pit type to be a tank. And once I've got it switched to a tank, I'm going to go change my size. I'm going to make that 1 meter by 2 meters. And I'm going to go give that another name other than new. I'm going to call that tank 1. So if we were to apply that one, you'll see that we now have another tank at the upstream end. Now those box culverts in between. Off to the pipe tab, let's go and select those as being box culverts. And we're going to put a height of 1 meter on those, and we'll put a width of 2 meters on that. Now, when I put these in, I'd like to have these fairly close to the ground surface. So on my design tab, I'm going to go put my cover limit to be 0.1, so just under the surface. So let's go and hit the set pit details on that, and we'll do a regrade pipes. Let's go profile this, and we'll see what we now have. So profile. Okay. Now, I apologize for those extra long flow conduits, but what I'm interested in right now is this upstream end. So there's my box culverts. The only thing that's changed in my design is that now my weir is trying to line up down here at the base, and I want that to be up near the top. Now, once again, I've talked about the fact that I wanted to keep these floating. So what I'm going to do is go back up to my design, and I'm going to change my drop mode. I'm going to change this to be a minimum drop. And it seems quite odd. I'm going to put a negative value in. So a negative 0.8 drop, if I go hit regrade, what that's going to do is instead of having the weir drop down, it's going to move up. So it's going to be 800 millimeters above the bottom of my tank, my culverts. So essentially what I've done is I've gone and converted my first design, which was done with a tank, over to the use of box culverts. So the last step to get this up and running is we need to go attach our hydrology back to the upstream end. So I'm going to go to my Catchment tab, use my pick button and go grab that. And it says that there's no catchments, and that's because I was on set number 1. Let's go to set number 2 where it belongs. And we can do a set catchments. Once again, we've got our area back. We said we wanted that to be 100% impervious. And we said down here last time we used 2. I just want to make sure I'm using the same parameters. One last design tip about doing box culverts. That is a huge cross-sectional area. And the water is going to be able to move back and forth very, very easily. And if you look at the results, you'll see sort of the water swashing from back and forth in that. It's going to be a very flat hydraulic grade line because we have very little flow. So one of the things you can do to help that out is to go to your pipe tab, go to the main, and you can increase the roughness. Now, as I said, a little extra roughness is not going to change the slope of the flows because they're very low flows in a very big tank, but it will stop the water from going back and forth and sloshing around a bit. It's a little bit of a design trick for that. All right, I'm just going to do a one-clack double check to make sure we're on the pit tab. I also want to make sure I change my KU values to be 0. We've talked about that a few times already. And we're ready to go do the analysis on that. So if we go to our analysis button and we go run that, now I could of course go back through and run my two-year ARI, the 20, the 50, and the 100, but I think for this session it'll be good enough just to see that we've got that up and running for ourselves. So back to the editor. The one bit that I definitely like to bring to your attention is if I go and select the tank like we always had before and went to my results, and same thing I always did. Look, I want to see all the design storms. Go check the elevation to find out which was our critical storms. Okay. For this one, it's telling me that the critical storm was the 25-minute storm. So what's happening when I'm looking at this is I'm looking at the flows down through the culvert. They've already been attenuated. So if I'm interested in looking at the total inflow and total outflow like we've done before, so let's go back to that 60-minute storm, for example. If I go see the total inflows and outflows, you'll see that inflow is quite jagged, okay? And if you remember our inflow from our hydrograph was 153, the reason it's 140 here is because at this end, it's already been attenuated by the storage in the tank. Let's go back and look at the other end. If I was to go back up here and we go look at the total inflows and outflows at the top end, that's where we see our total inflow of 153, okay? But you'll see that all the attenuation isn't happened yet because the attenuation happens both in the tank and due to the outlet control structures. So that's an important thing to consider is when you go back and look at these, that you've got your attenuation in your culvert happens in the culvert storage, first of all, and second of all, down in the actual control structures. So if I was to zoom in a little bit closer there, one of the things you will notice that's different is we'll get slightly higher discharges because the culverts are on a slope. Okay, we've got a 1% slope on those culverts, so it's not flat storage, bottom storage. There's actually a little bit of a slope on those culverts. So we're not going to get exactly the same answers between the two. Now, that concludes everything that I wanted to show you for today. It's a very full day of numbers and a very full day of theory. If you're not a true lover of hydraulics, I would assume you would have left by now. Only those that love all these details in design would have stayed to the end. So what we will do is we'll pause there and we'll open up to see if there's any questions.
Thanks, Rob. We have had some questions through. Alan in Melbourne has actually asked 2 questions, so I'll read these out and see if you can answer those. Can you integrate the underground storage design as part of a drainage network? So like low flow diversion pit to underground storage?
Really good question, and absolutely yes. What I've done inside this presentation was just isolated a very small component. What I would be doing, and one of the things I was sort of careful was to make sure that we had no backwater controls while I was doing this. But if I was to go and put on the rest of my stormwater model for the whole project, the very next thing I would do is go grab my outlet, drag and drop it into my stormwater network, and then it would become an integrated part of the entire stormwater network. So yes, to the first question, it can be part of the entire design, and it should be. It'll take slightly longer, of course, if I was solving for the entire network here, which is why I isolated it for this presentation. The second one is that diversions from here. I've got 3 flow paths between the control structure at the end of my tank down to my outlet pit. So that's only 3. If also I could have water bubbling up out of my grate, and then I would have bypass on the surface, and I could have bypass channels to take the major flows away. I could have the water going to a separate open stormwater pit if I wanted to do water quality. It would all be just about adding additional links. So yes to making it part of the bigger network, and absolutely no trouble tying it into water quality devices or anything else like that. So I hope that answers that question for you.
Wonderful. And also, will KU factors change to properly reflect the true losses when running analysis, or will it remain as set, so 0? That was one, Alan, as well.
Yes, Alan, if I put them in as 0, they will stay at 0. Okay. What happens is when we have water, in this case, we hooked up our catchments so that the flow is going to go from the building into the tank. If the water could be coming into the tank through a small pipe, it could be a piped connection. It could be through overland flow coming into the top over here. Probably not for such a long building. But the KU represents the losses at the upstream end of our conduits. And in this case, I would not want to have the Missouri charge doing those calculations. So 0 might be a pretty good value to use for that. Now, if I go down to my other structures that I have down here, a weir would never use a KU value, okay, because KUs belong to conduits for pipes. And nor would the orifice, because the orifice is controlled only by the discharge coefficient. However, we did have that 100 millimeter pipe. And that 100 millimeter pipe will have some entrance loss as the water comes through. So I guess in your answer that putting in a small KU value just for that 100 millimeter pipe might be a good idea.
Sure. Now, because of time, I'll just read out one more. Fung in Brisbane has asked, how can I model underground tanks with high early discharge pits?
Okay. Yep. High early discharge is a term that describes a whole variety of structures. When I first started the presentation, my very first concern was about high early discharge. And the very first thing I did on the high early discharge was I made sure that my tailwater was below my orifice so I could get rid of the water as quickly as I could. The second thing I did is I talked about having a drop between the storage location and my outflow orifice. That way I build up a head on the orifice immediately. And by doing that, once again, I get a high early discharge. So that high early discharge is all about getting rid of the water early so that we don't have a significant storage or between the inflow and the outflow. So yes, it's definitely possible. Now, sometimes when people use the term high early discharge to mean a pit such as this with a flap gate in between. And yes, if you do want to install those high early discharges with flap gates, be very careful that your authority approves of such a thing, because often they don't like mechanical operations inside stormwater pits. But if that was the case, we could do that, and we do that with the tick box on our conduits that say no backwards flow. So that's how we model the flap gates, if it was a flap gate you're referring to. So in summary to that, there's a lot of high early discharge tools or designs that you can use that do not involve a flap gate. So be careful with that. So short answer would be yes, high early discharge is a fundamental part of our design. So Fung, I hope that helps answer your question there.
Wonderful. Thanks, Rob. And thanks to the audience for your great questions. Sorry to anyone we couldn't answer live, but we'll get back to you individually afterwards. The recording of this webinar will be available in coming days through our website and our YouTube channel. Our next Industry Solutions webinar will be on road flow on the 20th of April to continue the Three Waters theme that's happening in the series at the moment. We've also got some great training topics coming up, so keep an eye on our emails and social media channels. If you need to contact us in the meantime, our details are on the screen now. That concludes our presentation for today. Thank you for attending, and we hope to see you at future webinars.